All right, hi everyone. Welcome to our asynchronous class for today. Sorry I couldn't be in person today, but the lecture is pretty short. We're just going to do a couple examples on mathematical modeling from 2.6. Remember, we started 2.6 at the end of our last class on Wednesday. So this is just kind of the wrap up, and we're going to do a couple of homework problems. And then your homework for 2.6 will open up today and it'll be due next Thursday as always. I'm also going to host office hours tomorrow on Tuesday. If anyone would like to join to ask questions about today's lecture, you are more than welcome to, or as always, welcome to send me an email with any questions that you have. Okay, so let's get into it. 2.6 on mathematical modeling. We're going to start with a problem similar to your homework 2.6 number 1. We have let P be any point xy. So we don't know what xy is, we just know it's some coordinate. It's a point on the graph of y equals x squared minus 6. And the first thing we want to do is express the distance of this function from the origin. So P is some point on this function, and the origin is our point 0, 0. So we want to use the distance formula, and we want to find the distance from any point on this function to the origin 0, 0. Just as a reminder, the distance formula is d equals square root of x2 minus x1 squared plus y2 minus y. I said y, I wrote x. That's my bad. y2 minus y1 squared is what that should be. And we want to write this in terms of x, right? So we want to write this as a function of x. We don't want to write this in terms of y. We want our only variable to be x. So we know our first point is the origin. So it's the point 0, 0. This will be my x1, y1 in my distance formula. The second point is some point on the function where x is just x and y is defined as the function x squared minus 6. So again, we don't want to write this in terms of y, we just want to write it in terms of x. So we're going to write our y and that coordinate in terms of x. And our y is x squared minus 6, and that x squared minus 6 is our y2. So this is our x2, y2 in our formula. So we have everything we need. We're going to plug it in, and then we'll have some simplifying to do. So we put in d equals square root of x2 is x minus x1 is 0 squared plus y2 is x squared minus 6. I wrote x2. It is x2, but it's really, x2 is just x. So we don't actually need the 2 there. That makes it more confusing. And then x squared, not x2. And then this is minus y1, which is 0. So we have x2 minus x1 plus y2 minus y1, and this should be squared. So this is our distance formula with everything plugged in. And we're going to simplify a little bit. So first of all, x minus 0 is just x. So this first set of parentheses becomes just x squared. X squared minus 6 minus 0 is just x squared minus 6 squared. And then x squared minus 6 squared does not mean x squared squared minus 6 squared, right? I'm not just distributing the square. I'm not just distributing the power of 2. What this means is x squared minus 6 times x squared minus 6. So there are plenty of methods that we can use to multiply out these two binomials. We're going to do that over here on the side so we can just kind of plug it into our formula. So x squared minus 6 times x squared minus 6, we're going to use our double distribution method. So we're going to distribute x squared to x squared. That's x to the fourth. Then x squared to negative 6 is negative 6x squared. So we distributed x squared to both terms. Then we're going to distribute negative 6 to both terms. I do negative 6 times x squared is negative 6x squared. Negative 6 times negative 6 is positive 36. Here I can combine like terms. I have two x squared terms. Negative 6x squared minus x squared is negative 12x squared. Feel free to pause at any point during the video today if you need time to catch up with the writing. I'm going to go pretty quickly just because we're not in a live session. So I'm going to plug this in, x to the fourth minus 12x plus 36 in place of my x squared minus 6 squared. So x squared plus x to the fourth minus 12x squared plus 36. And then this is almost fully simplified. The last step is I have two terms with x squared inside my distance. So I'm going to combine those terms. So I have x to the fourth, x squared minus 12x squared is negative 11x squared plus 36. Okay. So at this point, we have our distance, d, in terms of x. And if you need to pause to write everything down, please do that. I'm going to copy our distance up at the top of the slide, and then I'm going to erase everything so I can keep going with our next parts. So that's our distance, and let's erase. Feel free to fast forward if you'd like. Okay, so we have our formula for distance in terms of x. We want to know what the distance is if x equals 0. Hard part is done already. We have our formula. All we have to do is plug in x equals 0. So when x equals 0, our formula for distance becomes the square root of 0 to the fourth minus 11 times 0 squared plus 36. Both of these terms just zero out, so I have just the square root of 36. 36 is a perfect square, so the square root of 36 is 6. So the distance if x is 0 from the origin is 6. We can do something similar. If x is 1, we just replace the x in our formula with 1. So we have 1 to the fourth minus 11 times 1 squared plus 36. 1 to the 4th is just 1. 11 times 1 squared is just 11. 1 minus 11 is negative 10. Plus 36 is 26. And then if we take the square root in our calculator, we're going to round this to the nearest hundredth. So the square root is 5.099. That's going to round up to 5.10. So on our function, when x is 0, the distance is 6 to the origin. When x is 1, the distance to the origin is 5.10. Next, we're going to graph the function. So we're going to graph not the original function x squared minus 6. We're going to graph d of x. We're going to graph our distance function. And we're going to do that in a TI-84 calculator. So I'm just going to switch my screen over. And we're just going to type it in. So we do y equals, and then we have the square root, that's second. And then the x squared button, we have that blue square root there. And then x to the power of 4, cursor out of the exponent, minus 11 x to the power of 2, out of the exponent, and then plus 36. And we can look at our graph. We don't need to adjust the window this time. It looks like we can see a good portion of our graph. We can see where it reaches a minimum, a local maximum, and then another minimum. And so this is representing the distance from a point on our original function to the origin. So right here at 0, looks like 0, 6, my distance was 0. My distance was 6 at x equals 0. And that's what we found, right? We plugged in x equals 0, we got a distance of 6. So we have our x, and then our y is the distance. Okay, so I'm not going to go back, change my screen back, but our next part of this, part E, is asking for values of x where the distance d of x is the smallest. So I'm going to leave it on the graph here because we're going to use the graph to find our minimums. So where the distance is the smallest is where the distance function, this graph, is at its minimum. And we have 2 points that look like they're at the minimum. So let's figure out what x is equal to at those points. And to do that, we're going to hit second and then calc. Number 3 is minimum, so we're going to hit 3. And then we follow the prompts on our calculator. We find the left bound, somewhere to the left of the minimum, the right bound, anywhere to the right of that minimum, and then a guess. And we have a minimum at negative 2.345, so that's about negative 2.35. We can repeat that process for the second minimum over here. We would do second calc. Number 3 is minimum. Find our left bound, right bound, and our guess. And this minimum has an x value of 2.345 again, so we're going to round that to 2.35. So there's 2 minimums. One is at negative 2.35, the other is at positive 2.35. And I'm just going to switch back over to my slideshow to write that in. So for what values of x is d of x the smallest? And that was, again, x equals negative 2.35 and positive 2.35. Again, feel free to pause, rewind, fast forward through any parts that you need to. This next slide is just for you guys on Canvas, just the picture of the graph and the minimum on one side. And then we're going to go to our next example. So our next example is, again, from 2.6. This is really similar to homework number 4 in your 2.6 homework. And our setup is a rectangle has one corner in quadrant 1 on the graph of y equals 36 minus x squared. Another at the origin, a third on the positive y-axis, and a fourth on the positive x-axis. So we're creating some rectangle. Here I have it drawn out, but I can really change. The only thing I know about this kind of fourth point, this fourth corner, is that it's somewhere on this graph. So I could change the shape of the rectangle if I kind of were able to kind of click that and slide it up or down. We don't know exactly where it is. It could be all the way up at the top. It could be all the way down here at the bottom. We don't know where that last corner is. We just know it's somewhere on the function. And then where these other two corners are going to kind of depend on where this fourth corner is. So we want to first find an expression for the area of this rectangle. We want to express it in terms of x. So again, I don't know the exact distance. Right now, I can ignore the numbers on my x and y axes. All I know is that this distance of the base of my rectangle is x. And it's going to change depending on where my fourth corner is. X can change. So right now, x is 5, but that's not always the case. Or x is 3, but that's not always the case. The height of my rectangle is going to depend on where this point is, right? So if I slide this down, my height's going to change. My height is y. We want to give this formula for area in terms of x, though, so we're going to write y in terms of x. We know we know y is 36 minus x squared. So if area equals base times height, the area of this rectangle in terms of x is x times 36 minus x squared. We could also multiply this out and say our area is 36x minus x cubed. Okay. So that's part A. Part B is finding the domain of this area function. And one way we can do this is by graphing, but when we graph, we have to really know what we're looking for because this function isn't just some equation, it's actually modeling something, right? It's modeling the area of this rectangle. And what I know about the area of this rectangle is that it can't be 0 or it can't be negative. So the area itself has to be greater than 0, can't be negative. I also know that my width, x, can't be 0 or negative either, then we wouldn't have a rectangle. So x has to be greater than 0. So we're looking for a domain here. We're looking for our restrictions on x. We know one restriction on x is that it has to be greater than 0. And then if a has to be greater than 0, that also means that 36x minus x cubed has to be greater than 0. And so I can kind of solve for this in a lot of different ways. I can solve for this by graphing 36x minus x cubed. I can solve for this by factoring and seeing where this is going to be equal to 0 for then when it's going to be below 0. Let's graph it because our next step is going to be to graph the function anyway. So let's go ahead and just graph it to figure out where this graph is greater than 0. So again, I'm going to switch my screen back over to my calculator. Right now I have that last graph I worked on, so I'm going to go back to y equals and clear that out. And then I'm going to type in my area function, so 36x minus x cubed. And then graph. And right now I definitely can't see my whole graph. We're going to adjust the window in a few minutes, but I also don't need to adjust my window for this question, right? Because I'm asking, where is the function greater than 0? And the function is greater than 0 between x equals 0, or it's above that axis, and x is 6 at this intercept. It's also greater than 0 over here past -6 on the x-axis. But we already said x can't be negative because x is representing our width. So we can ignore anything past 0 on the x-axis. So my domain restriction here, where my area is going to be positive, is between x equals 0 and x equals +6. So to write my domain, say that my domain is between 0 and 6. Or we could write this as 0 is less than x is less than 6. Right. And then, like I said, we're going to be graphing for part C. So we already graphed our function, and then we want to figure out for what value is A the largest. I'm going to erase a little bit here. And so we're asking for where's our maximum, at what value of x are we going to have that maximum? And so in order to find that, we are going to need to adjust our window in our calculator. So we already graphed our function. We're already on our graph, but we're zoomed out pretty far. We really only care about the positive portion of this function between x is 0 and x is +6. So we don't need to adjust our x-axis any. We're fine with that viewing window. But I need my y max to increase so I can see the top of my function there. So I'm going to go to my window, and I don't know where it is, but I'm going to scroll down to my y max, and I'm going to try out 100. And then graph. And that worked out. I can now see the top of this curve. So now to find the x value for my maximum, where area is the greatest, I'm going to hit second and calc. Number 4 is maximum. And then again, I follow the prompts. I choose my left bound. I choose my right bound. I choose a guess, so somewhere between those. And then I get my x and y values at the maximum. So the x value, or the width that would make this rectangle have the maximum area, is 3.46. The area itself, the maximum area, is 83.13. Or actually, that would round up, so 83.14. so switching over one more time. The way I would answer this, say for what x value is A the largest, that x value is 3.46. Part D asks us, what is the actual largest area? That was that y value at the maximum. So that was 83.14. Okay, so the solution is also written out just so you guys have this on Canvas as well for the next few slides. And then that is it. So like I said before, a really short lecture on mathematical modeling. Nothing super new, just kind of putting all of our concepts together, really getting comfortable using the graphing calculator to find our different pieces and write our functions. Please send me a message if you have any questions. Thanks for watching, guys.